All right. Thank you very much for the very kind introduction, David. It is such a pleasure to be here today. I have two affiliations up here. My current one, Reed College. I'm a new transplant out to Portland, Oregon. If you met me before August of last year, you might remember me being affiliated with University of Maryland. And I'm sorry, Maryland, but the logo needs a little work. I don't know. I like the Griffin better. So I'm delighted to be talking to you today about a paper that was joint work with several of my collaborators on throughput-efficient hybrid asynchronous consensus. And if you are familiar with those words, but not in that particular order or configuration, don't worry, we will get there. So just to get ourselves situated, because whenever we talk about blockchain or consensus, that's a whole big wide world of things, and you might be talking to someone for a good 10 to 15 minutes before you start to realize that you have completely different sets of definitions and expectations and settings and so on. So let's get that out of the way right now and say that today's talk is going to take place inside this Venn diagram circle of what I'm going to call classical BFT style consensus, which means that Nakamoto's protocol and Bitcoin are somewhere out of shot here. So permissioned protocols, the 5 servers at Google model, if you prefer. And I guess I'll call my research happy place, as you alluded to in the intro, is sort of how do we get the best possible safety and performance guarantees given the actual network conditions at the time that we run our protocol. So within that large and sort of fuzzily defined circle, we have what are known as optimistically responsive protocols. And we'll get to what exactly those are in a second, but the hint is kind of in the name. So they are optimistically going to start out on a plan A, and if things go wrong, then they'll turn to their plan B. And then lastly, within this big space, we have a subset of asynchronous BFT-style consensus, meaning protocols that are going to make limited or very few timing assumptions about the messages being delivered between parties. We'll get more formal about all of this soon, but the talk is going to be right here. So I just wanted to get ourselves all in the same landscape. Yes? That is a great question. So the question was, aren't all optimistically responsive protocols, or sorry, aren't all asynchronous protocols optimistically responsive? And let me think about that for a moment. I have a suspicion that I could come up with a straw example, but I don't know that I could do it on the spot. So I think I might defer that question and circle back around to it. Is there something that stands out to you in particular as, so is the question, isn't asynchronous contained in optimistically responsive? Yeah, okay, yeah, that's fair. I think for the purposes of the introduction, what I care about folks taking away is that there exists an intersection. So I think I'm gonna punt on the question and get to it. So our work specifically is this work called Abraxas, Throughput-Efficient Hybrid Asynchronous Consensus. And it was with these wonderful co-authors, Jonathan Katz, Julian Loss, Kartik Naik, and Simon Ostenreiter. And just to get the question out of the way, what the heck is Abraxas? Well, the Wikipedia page is not particularly enlightening, but it is sort of a magic word like abracadabra almost that appears on amulets associated with hybrid creatures. So I thought the word sounded neat, Julian thought the meaning was cool, and here we are. So to give you the motivation, I'm going to use an analogy. So to me, the promise or the appeal of an optimistically responsive asynchronous protocol is like driving in a snowstorm, or rather, how should you drive in a snowstorm? So let's say that you need to drive to the airport, but there's a chance of heavy snow. What do you do to arrive safely and quickly? And this is the US. We have cars on the brain. We're going to assume that there's no public transit. So let's just get that out of the way. You got to go by car, sorry. So option A, you're not worried about a few snowflakes, drive normally, usual speed, no snow chains on, no matter how hard the snow gets. This is disclaimer, don't do this. And someone tell my neighbors back home not to either. So option B, it's It's better to be safe than sorry. We're going to drive carefully with snow chains on, high beams, 5 miles per hour all the time, even before it starts snowing. Okay. All right, option C is respond to the conditions. Drive normally while the weather is good. If it starts to snow, pull over and put your snow chains on. Drive cautiously until it is safe to drive normally again. Okay? So let's sort of translate this into the actual context, because I'm not actually here to teach you how to drive. So you need to reach agreement in an asynchronous network, i.e., messages between devices may be delayed arbitrarily. So if you're not worried about a few message delays, maybe you use a synchronous or partially synchronous protocol, but naturally, these lose some or all of their guarantees if the network is asynchronous. So this is, again, like the driving example, not something I endorse. Better safe than sorry, use a fully asynchronous protocol. This, in my opinion, is in a lot of cases a perfectly reasonable solution, but we might be interested in exploring some of the design space where we explore some of those trade-offs more deeply. So let's say that we're interested in developing a protocol that responds to the conditions. We're going to start by running a synchronous or partially synchronous protocol. Specifically, we'll call this our optimistic path, and we'll monitor its progress somehow. And if it fails, then our hope is that we can gracefully shut down that path and all agree to hop over to our other path. Now, the spoiler, or sort of where we're going, is that protocols of this type C, which I'll get to in a moment, which I'll call the canonical optimistically responsive asynchronous protocol, sort of have certain weather conditions that really just drive their performance into the ground. There are certain flurries where they just get absolutely nowhere fast, okay? So we're going to say, can we sort of keep this nice trade-off and also eliminate a sort of historical weakness of the canonical approach to this type of protocol? So just to give us our outline. So chapter 1, background and motivation. We've already sort of started on that. We're going to meet our friend, the canonical optimistically responsive protocol, in a little more detail. I'm going to sort of motivate or try to convince you that there are specific scenarios in which that option C is suboptimal. There are conditions where it struggles. And then that's going to lead us to chapter 2. What did we do about it? So that is our protocol, Abraxas. And the short answer is the canonical protocol puts 2 paths in sequence. We're going to put them in parallel. Oh my gosh, hold for applause. All right. There's actually other recent work that I'll talk about that takes a similar approach. And overall, I think that different ways of composing paths beyond the canonical one after the other protocol are sort of represent a new and really exciting design space for this type of protocol. So then last but not least, there's going to be a quick epilogue where I get into some sort of things that happened after the conference. So whether you've never heard of this area of work, or whether you were at the front row at the CCS talk, which I didn't give, so I actually have no idea what it went on. I'm hoping that this will be somewhere, some combination in the Venn diagram of informative and entertaining, whichever of those folks you are. Okay? So let's just, again, get square on our goals. So in this talk, our goal is what I'll call or what many people call state machine replication. So we're going to think of state machine replication, or at least the ideal thing that we want to emulate. Thanks, Juan, for earlier setting up the abstraction there. The ideal thing that we want to emulate is a black box where unordered transactions go in, ordered transactions come out. Specifically, in this talk, we'll use the abstraction of an ordered append-only log that gets blocks added to it of transactions. And I've specifically used pretty meaningless transactions because the actual semantic meanings of the values for this talk are somebody else's problem, not ours. They are giving us unordered things, and we are ordering them, and that is it. Okay. So that's what we want to do, but unfortunately, in consensus, we are given a bunch of imperfect parts to do it with. So we are going to have a bunch of servers who together are trying to emulate this picture on the left. And to make matters worse, some of them are going to be faulty. Some of them are going to misbehave arbitrarily. And in our asynchronous setting, we know that optimally the best we can do is have at most t less than n over 3, strictly less than n over 3. We're going to assume that we have nice cryptographic tools like public key infrastructure and so on, just a little asterisk there. And we have point-to-point channels, as earlier talks mentioned. We don't have broadcast or a bulletin board for free. If we want that, we've got to build it. Lastly, we're working in an asynchronous network. The message delays are adversarial and unbounded. Feel free to jump in with any questions, folks. All right, so that's what we want, and that's our tools. So what does this look like locally? So locally, some unmerged transactions are showing up on the doorstep or in the inbox of some server. And that server is going to send messages to all of its server friends. And then it is going to have a local version of this log, and which we denote with the subscript I. And our hope is that any two non-faulty servers have the same blocks at each index of their log. And furthermore, that anything that is input to all non-faulty servers eventually gets output by all non-faulty servers. So there's a little asterisk here where you can define this slightly differently and say if any non-faulty server receives it, then it should be output, but you usually just get around that by using some sort of gossip protocol. Lastly, and this one is ever so slightly non-standard, but it turned out to be a convenient way to state the property for our proofs. For all k greater than or equal to 1, all non-faulty servers eventually output block k. So this just means that essentially the log continues growing. We never reach a point where the log just ceases to grow. Link?
Why does liveness not imply completeness?
So let's see. In my mind, the reason why this doesn't imply why completeness is not implied by liveness is that someone could have a ghost block that, let's say, some party doesn't output block number 4, but eventually they have some other block that outputs the thing. And if you have, I suppose if you have safety and liveness, then you might be safe because you can't have that transaction, you can't have different blocks of those areas. But essentially, we find it convenient in our proofs to break it down in this way. Good question. Okay, so I said a moment ago that we have to make do with a bunch of imperfect servers as our building blocks. And that's not entirely true because I'm a theorist and I don't like dealing with nasty, messy, realistic things. So instead, I'm going to assume that somebody has built nice things out of the nasty, messy things. And now my only job is to plug a bunch of them together into some other nice thing. Okay, so somebody else has done all of the hard work of building nice SMR abstractions from messy parts and real world computers. And we're interested in protocols that glue or duct tape or rope all of those together in some way in order to get presumably some nice combination of their properties. And in particular, often the sort of main components here will themselves be state machine replication protocols. Sometimes there'll be a weaker primitive. We'll get to that in just a moment. And there will also often be sort of an assortment of helper protocols, maybe just a plain Byzantine agreement protocol, something like that. We're usually going to omit those unless they're super, super critical. Okay, so it's time to meet one of the main characters of this talk, which is the canonical optimistically responsive asynchronous protocol. This is one of those plug and play protocols where you have an optimistic path and you have a fallback path. And the exact properties of this provable, what I'm calling a provable optimistic path, are going to vary, and I'm not going to worry too hard about covering every paper that has come out with this one generalization. But basically, this is something that's high performance in some optimistic case And otherwise, in the very worst case, everything falls apart. We're just going to require that it is provable in some sense that it is the writers of those papers' job to define formally. But for example, an example of what I mean when I talk about a provability property is something like there is a quorum certificate that proves to somebody else that a sufficient number of non-faulty parties think this is really a legitimate output by the protocol, okay? So for example, an example provability property would be, say, for example, a valid proof exists for block B, i.e. there is some string that I can show you to convince that this is a real certified block from the protocol, if and only if at least some number of non-faulty servers actually output that thing at that spot, okay? On the other hand, those tend to be a bit more bespoke. The async, or the fallback path is typically just an asynchronous Byzantine fault-tolerant state machine replication of this variety I just explained. Sometimes it has a provability property, and I'm not saying that isn't important, but I am saying I'm not going to talk about it very much in the details here. Okay, so a very brief, I should talk briefly about how it glues those together. So essentially, our plan A is to run our optimistic path. If we detect that something has gone wrong, that's one of those little hidden sub-protocols here that I'm not showing, then we're going to run another little not shown sub-protocol that tells us sort of, that syncs us up to some point in our logs, and then we're going to get on the fallback path and go from there. So founding works here include Kursawa and Shoup and Ramasamy and Kashan around 2005. There's been a lot of interesting stuff that I can't possibly fit in this talk, including the next 700 BFT protocols. And then in recent years, this design paradigm has really been pushed farther in Bolt-Dumbo transformer and Jolteon and Ditto, for example, where we sort of really push the round complexity in particular of these building blocks down so that those helper protocols are as lightweight as possible, and we spend as little time as possible sort of spinning our wheels. I'll say more about that in just a moment. Okay, so I find that it helps a lot to see an example. So let us walk through sort of, this is where the canonical protocol shines, is in this sort of example. So let's say that it starts out sunny, returning to our weather analogy. The fast path is chugging along, doing great. And then we hit some bad weather. That could be message delays, that could be a leader goes offline. Our optimistic umbrella sort of varies, but you can think of that as bad weather in the network. And that fast path is going to crash. It's not built for that. There's then a little delay, unlike probably in the driving analogy. The analogy breaks down a little here. Usually it's pretty obvious when you've crashed your car. In this case, we're often not able to directly measure the network weather in the same way that we can look outside and see that it's snowing. Usually we are indirectly seeing that something has gone wrong down the line. We're seeing, oh, it's been an hour, there should be a new block. Where is that new block? And so that's that gap there, where there's an hour where we say, oh wait, shouldn't something have happened by now? And that whole time we've been sort of sitting there on the side of the road, not making progress. So once those protocols detect the crash, everybody sort of compares notes on what happened with their primary path and sort of gets synced up on that. And then once you've done that, you can start running your secondary path or your fallback path.
So what can go wrong on the snowy day and then you detect it? It's only liveness violation, it's not safety violation.
So let's see. So there's sort of an asterisk here, which is, for the purposes of this talk, we're assuming the provability property sort of covers the possibility of a safety violation. So in our paper, we only assume, or we really don't assume anything of the fast path, and we tack on a provability property on top of that, so that if enough honest parties, or sorry, non-faulty parties are willing to sign on that a block is legitimate, then there cannot exist two different certificates for that same block. So asterisk is, in our paper, there's a version where we require nothing at all. In the talk, for simplicity, we're assuming that our fast path only gives us the provability property. Okay, so this is the good case. And if we were just running a plain old asynchronous protocol, which is being used on the backup path there, we would see something like this. So basically, the time that we lost having crashed our car, this is not a good lesson. Do not take anything away from this. The time that we lost having crashed our car was worth it because we went really fast the rest of the time. I didn't realize that would be the moral here. I swear, okay, let's keep moving. So I'm gonna skip this example and go, this is sort of a medium example, and I'm gonna try my best to go straight to the more extreme example. Okay, so that was the good case. Here's where that protocol doesn't do so good. So if the fast path always crashes, then we're only actually making progress after we do all that dragging our car out of the ditch and then running the fast path. We would have been way better off just running the fast path, okay? So essentially, with this protocol, we end up in a situation where we have regret or we have buyer's remorse. We wish that we had just taken that asynchronous protocol and actually made progress instead of spending all of our time pulling our car out of a ditch, okay? So that is the weather that makes this case, this protocol sort of snow chain purgatory. They're always putting on snow chains. I didn't think about how all of these animations would make it hard for me to fast forward.
Take the optimistic path.
Is there one? I don't see that on the remote.
Optimistic.
Okay. Get ready. Everybody, hold on to your hats, because if you saw some nice slides this morning. So cars crashed. Meanwhile, the fallback path is doing great. We really wish we had been in that car instead of this car. What if we take our grappling hook and our pair of skis, and as soon as we see that fallback path escaping out ahead, we ready, aim, fire the grappling hook and ski our way all the way ahead to where that path was. So that's the idea of Abraxas here. We have our paths in parallel and we get rid of regret eventually with some delay. It takes us time to all agree to fire the grappling hook at once. You want to make sure that people aren't sort of all over the place with that. Otherwise you get into an even worse situation. But once you do, so you're trading some latency for some throughput. I'm going to skip through this to some more interesting things. I'm at 2 minutes, David? 2? Okay. Alrighty. So I think the main idea is things are in parallel rather than in sequence. And honestly, to me, I think the motivation of this paper was the part that we struggled the most with and the part that I think is most interesting. I think once I get through that, it's like, oh yeah, put them in parallel. Alrighty. And there are some technical details that you have to take care of. Notably, you have to agree when the optimistic path is or isn't the right place to be. And you have to safely sort of grappling hook over. I'll skip through some of those technical details. I'd be happy to answer questions about it afterwards. Sorry?
Asynchronous, right? So you have like different core sets in both paths?
Let's see. Different core sets. Here with core sets, are we talking about parties or? Yes, so we typically have a leader-based optimistic protocol and
Coordinator for both person?
not exactly. So let's see. So the asynchronous protocol in practice is usually not leader-based. Everyone is proposing blocks. Yes.
So there might be different core sets in each person.
Yep.
And so the input, the output might be different.
Yep. We're making no assumptions about the order in which things come out the other side of these two state machine replications. As far as the sub-protocols are concerned, as far as the plugin SMRs are concerned, this protocol doesn't exist. They're completely oblivious to the existence of our protocol running on top of them. Great question.
We're running a little bit.
Sorry?
Running a little bit on time.
Okay, so ready the grappling hook. I think you guys get the idea of this one by now. But essentially, see, we are taking longer there. Oh. So we're adding some latency here. But when we do sort of finally fire the grappling hook, we zoom way ahead. We've gotten rid of that regret that we had before, because however long we're spinning our wheels, we're eventually able to zoom to catch up with it. So we had all of these nice metrics of interest that I'll show you really briefly. So communication complexity, we had bits sent by all parties per block, worst case latency. Then we had experiments, because our reviewers said we should have experiments. And
You sent to CCS.
okay, you're right. That's on us. We did send it to CCS. Fair enough. Fair enough. So the epilogue, very quickly, is that I think I am very smug about the fact that we designed a black box protocol for the reason that Matthew Rambeau found a bug in one of the, at the time, state-of-the-art plugin things that we were using. And if we had gone and done a bespoke protocol that was intricately woven into that plugin, I would have, oh my goodness. I don't even want to think about rewriting those proofs. They were bad enough the first time. I was so glad that I could just say, okay, here's another plugin thing that also satisfies those guarantees, and I am good to go. That's a 5-minute paper edit right there. I mean, not literally, but you get the idea. So I was pretty smug about that. So at the time, everybody, it seemed like, was using 2-chain VABA. There was a bug in it. Swap it out, you're good to go. This is one reason why we designed it as a black box compiler. Also to just, even if there's no bugs, you can easily update to the state of the art, and it made the theorists happy. I'm the theorist, it's me. Disclaimer, I'm a big fan of Jolteon and Ditto. This is not meant at a dig at them at all. The bug was in their paper. If I see so much as a single tweet suggesting otherwise, I'm going to be really mad, okay? So a big shout out to folks who are doing really great work in this area, which includes, but is in no way limited to, all of these fine folks.
All right.
Okay, if you liked this talk, or if you didn't, but in a constructive way, please come find me or email me, sorry. If you didn't like this talk in an unconstructive way, please direct your comments to my wonderful co-authors. Thank you so much.